convert this h. Right? So now I want to make you a simple exercise. If I define a signal h bar like this, then now I want to find out what is the h bar of omega have to be. Right? I have to define what it is. So h bar of h omega now is just simply summation in hn. Summation in hn. And then have E minus J omega n. But now anytime I have H, so n is a running variable, and now I just simply minus n. Okay. And of course I can make a change of variable n equals n minus, so I can put this and then I do the plus n. The same, okay? One thing I make everything simple for you here is I assume everything is real. Signal here is real. So this technique is real. If you want to do things in complex domain, then maybe you have to take one at a complex conjugated value. Just a side note, in the homework actually I do the complex conjugate. But now we assume that, so let me put here. Assume, okay. We assume h and is real. It's real, right? It is real. So it is real, then we want to see what is the difference between this and the h without the omega. So you see, in the exact same sign, except now instead of minus, I have a plus. Right? So we have something e to j something, and I instead of minus, I have a plus. What did I do? I did the complex conjugate. I did the complex conjugate of that number. And if I take the complex conjugate of that number, I take the complex conjugate of that number, and I multiply all the real, so it doesn't change, right? So this thing here, going to be equal to the h of omega, but now I take the complex conjugate. Right? Because h of things is a complex conjugate of e j omega n. Everybody see that? So, if that's the case, then from now we can find out that the convolution now is product of different the convolution now in frequency domain is very simple because now we just have a product. So the gamma of y of omega is simply equal to h of omega times h of omega, and I take the complex conjugate, and I take the gamma of x of omega. Okay? I can even simplify that a little bit. If I take a number multiplied with its complex conjugate, what would I get? You got the take omega squared, right? You have see if I take a plus bj have a minus bj, right? Then this equals just a squared plus b squared, which is the magnitude of the complex number. So this, I can write that equal to h of omega squared times gamma of x of omega, which is a very powerful theorem. So I throw away that plot, but remember that I have, maybe I should draw again our figure. So this is the system. The system x is a fixed. This system I have x. And to describe that, I can use the autocorrelation function of that. And to describe this y, I can use the autocorrelation function of y. Because now it is a y-stationary process. And the y, the gamma of y is related to gamma of x and h through this, or in the Fourier domain is related by this. Okay, so that. Any questions so far? or precisely we just borrow them by the function, autocorrelation function. And some of the similar concepts in signal processing can be mapped out to this autocorrelation function either in time or frequency. Okay, so now we take a break. After the break, we come back and see now maybe those randomness can allow us to develop filters or some processing. Okay, so let's with the foundation of random variables and random processing or random signals, we're now going to utilize in signal processing. And just before the break, I show you one very key result, and you can see how this concept can be put to use in the context of signal processing. Right? We not just use this as mathematical concept, but it is now become a signal processing tool. All right. So the next thing I want to now, quite a remarkable property, very remarkable property of designing filter, so-called the window filter. So the concept is the following. Here the black box I need to design, and it is a filter. It is a filter edge of n. And to make it simple, I let n go from n 0 to n minus 1. So I have a length n filter from 0 to n minus 1. And we need to design this filter. So in the thing we learned yesterday is a deterministic framework where I can specify the requirement of this filter based on its frequency characteristic. That means I do have a general model for the signal and I want to filter out certain frequency and I can design a filter. So now in the stochastics of the random framework, we could also design a filter. So I have a signal xn now. But now, I don't know a particular instance, but I know a whole process. And so this thing here is a y-set stationary process. So of course I have a random signal, I would have a random output. Y-n. Okay. And I do wish now that, so this is output, so this is output. And I do wish now that there is a design, so this is a design output. It is a desired output that I wish that a signal will go through and will output something like this. But of course, the desired output, the signal is random. It's a random, different value. So this also has to be a random signal. And now, what I wish to have is I wish to have study design output. And here's the actual output. So this is actual output. And for that,